Welcome to this explainer on mastering the counter variable for iteration. Let's get right into it, because if you're writing generic algorithms in your Cambridge IGCSE Paper 2 exam, you are going to lose critical marks. And honestly, the absolute worst part about this, most students don't even realize why it happened until the final grade boundaries are released and it's too late. So today, we are jumping straight into the deep end. We're going to fix a very common coding mistake that could literally cost you an entire grade boundary. Picture this scenario. You're in the exam and you write out a classic exam trap. Output, student, counter. Now, at first glance, that looks totally correct, right? I mean, intuitively, you'd use a counter inside the brackets to go through a list. But actually, this logic is completely flawed. This code triggers a massive error right out of the gate because the counter variable is entirely uninitialized and it's unbounded. Basically, the loop just lacks any kind of logical control. It's kind of like telling a robot to take a step, but never telling it where to start or how many steps it actually needs to take. It's just going to crash. So, why exactly did this generic piece of code fail to output the array student 0 through 19 correctly? Well, if you're relying purely on standard revision techniques, this looks like a perfectly fine textbook line of code to write down. But here's the thing. Cambridge examiners are absolutely ruthless when it comes to array iteration. To fix this, and more importantly to secure your marks, we need to reverse engineer the logic here. We need to start with the very foundation of what controls this entire process. Let's just rebuild this whole concept from the ground up.
Okay, let's dive into this. At its core, a counter is simply a variable used to keep a record of the number of times an action occurs. You can think of it like the ultimate tally system inside your computer program. Without this tally, standard methods of solution, things like awarding a mark to each student or printing a list of names, they just completely fall apart. Why? Because your program has absolutely no working memory of how many times it has actually executed the job. It's totally flying blind.
And that fundamental concept brings us directly to iteration. Iteration is basically just repeating a sequence of instructions using a loop structure. But here is the absolutely critical connection you need to make. Iteration is entirely dependent on the counter to track its progress. The loop structure relies entirely on that counter to determine exactly when the repeating action should stop. Because if the counter isn't explicitly set up to say, hey, stop at 20, well, your program is either going to crash immediately or it's going to loop infinitely until the system completely runs out of memory. Now in a moment, I'm going to show you a hidden examiner clue that changes the answer completely. And trust me, missing this specific detail will severely cap your final score on paper 2. And that's regardless of how perfect your programming logic actually is. But before we get to that hidden clue, we really need to build a framework that makes that clue obvious in the first place. So how do we actually construct these loops?
Looking at our source material, it highlights two primary ways to set up these loop structures. You've got the precondition loop and the postcondition loop. A precondition loop tests the counter at the very start of the loop, meaning if the condition isn't met right away, the loop might literally never run at all. On the flip side, a postcondition loop tests at the very end, which guarantees that the code runs at least one single time. So exactly where you place your counter test completely changes the entire logic flow of your algorithm. It's a huge distinction.
So, let's apply this to the specific constraints of our scenario. We need to output exactly 20 student names. Not 19, not 21, but exactly 20. And these names are stored in the array student 0 through 19. Now notice the syntax there. The array index starts at 0, not 1. This is a super common trap. It means our counter variable must perfectly align with those exact index positions. It has to step from 0 all the way up to 19, which, if you count it out, ultimately results in exactly 20 iterations.
Now, what's really interesting about this mapping is how the relationship between the counting variable and the stored data is so critical. Notice how the counter variable must map perfectly to the array index with every single pass in this trace table. Look at iteration 0. The counter is 0, and we output student 0. In iteration 1, the counter is 1, and we output student 1. Makes sense? If your loop doesn't explicitly initialize that counter at 0, you are going to completely skip the very first student in the array. Using this kind of visual trace table reasoning is just an absolutely essential skill for checking your logic.
All right, let's pause for a quick 60-second retrieval practice checkpoint. Keeping a record using a counter is vital for sure, but remember, it's just one of several standard algorithm methods that you need to master. We've also got counting, totaling, which is basically adding a new value to a running total every time an action occurs, and finding the maximum and minimum values within a list. Our focus right now is counting, obviously, but just keep in mind that the counter variable is really the driving engine that makes all these other methods possible inside a loop.
So, how do we take all this foundational knowledge and transform it into a flawless, full-mark exam answer? Well, We use the 4-step mark scheme upgrade framework. Step 1, you identify the concept. Step 2, you pull the specific evidence or data constraints straight out of the question. Step 3, you apply your logical scientific reasoning. And finally, Step 4, you utilize precise examiner wording. This right here is the ultimate framework for structuring those top-band answers, and it perfectly sets us up to solve that initial broken code we looked at earlier.
Okay, it is time for a quick interactive challenge. I want you to pause and predict. How do we fix that initial flawed loop using our new framework and the scenario nouns? Think about it. How do you apply the actual specific data we've discussed? How would you initialize the counter at 0, test it against the number 19, and output the exact array? Take a second. Do you have your mental draft ready? All right, let's look at the actual fix. And this brilliantly illustrates the massive mark difference between a weak generic answer and an upgraded scenario-specific answer. Look at this. A generic broken loop that simply states something like print the students might literally get you 0 marks. But a complete top-band answer, it explicitly uses the scenario constraints. It initializes the counter at 0, creates a loop that runs until the counter reaches 19, and outputs the exact array syntax, student, counter. Doing this proves to the examiner that you are actually applying computational thinking to the problem, not just reciting memorized theory.
Remember that hidden examiner clue I promised you earlier? Well, here it is. The clue is always hiding in plain sight within the Paper 2 command words. Whether a question asks you to state, describe, explain, or show, the absolute secret for full marks is to respond accurately to that specific command word while aggressively using the scenario nouns. If the exam gives you an array named student and you write a perfectly functioning loop using a generic array named names, you are going to lose the marks. The scenario constraints are your ultimate hidden clue to unlocking that top grade boundary. To ensure you never miss out on these exact mark-saving strategies, make sure to subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We are continuously breaking down every single corner of the syllabus to make sure you have the elite tools you need for exam day.
But wait, our journey isn't quite over just yet. Okay, so we fixed the loop, your counter works perfectly, and your array outputs exactly 20 students without throwing any errors. But what happens to your iteration if a hacker intercepts your unencrypted array data right in the middle of transmission? We've completely mastered the logic on the screen, sure, but the data itself is exposed and totally vulnerable. And that brings us to the next hardest skill on the syllabus, cybersecurity risks. It's a huge topic where even top-tier students drop crucial marks. You absolutely must watch our next explainer to see how to secure the very data your loops are processing. I'll see you there.